So I'm really happy to be back here after a few months. So I was asked to talk about black holes in string theory. So let me begin by, so today, in fact, I'll just try to state the problem that we'll try to address, and maybe as we go along, we'll see how things are done. Is this visible at the back? Okay. Thank you. So I think I'll begin by reviewing the basic aspects of black hole thermodynamics, which we have already studied last week. So the simplest black hole solution, in fact also the earliest, is the Schwarzschild. This all of you have seen Schwarzschild metric. Yes? No? Okay. So let me just see the speed of light. G is a Newton's gravitational constant. M is the mass. And P r theta phi are the space-time coordinates. Okay, this is the way one writes the Schwarzschild metric. So this metric apparently is singular. Okay, because had r equal to 2 gm over c squared, this quantity is 0, and hence it gives you a divergent result. But we know that this is coordinate singularity. Which means by changing coordinates, instead of using the RT coordinate system, you can change your coordinates so that the singularity goes away. The metric looks completely smooth. So this means, so this is coordinate singularity. So if someone goes through okay, you can go into a spaceship and jump through the r equal to 2 gm by c square, and you will not really feel anything. Okay, except the regular gravitational force that you of course always feel. Okay, that's the meaning of the statement that this is a coordinate singularity. That there is really no genuine obstacle at this surface. Nevertheless, this is something special because while you can jump through this surface, once you have crossed it, you cannot come back. So, okay, and this is what is described by saying that R equal to 2gm over c square is the event horizon. Is this familiar to everybody? And you probably also saw the Penrose diagram yesterday, right? So we did the Penrose diagram to show that this is really like a one-way membrane. So this is a one-way membrane. But I forgot to mention that if you have any questions, please feel free to ask anytime. So this means that if we look at such an object in the sky, we'll not see anything coming out of the object, right? Because it absorbs everything, emits nothing. Okay, so this surface R equal to 2gm over c square absorbs everything and emits nothing. And this is the reason this is called a black hole. That if we look at this object, we'll see a black patch of sky in that over the R equal to 2gm over c square surface. But this changed. Oh, maybe I should have also said that we can calculate the horizon area. So horizon area is 4 pi r square. Maybe I can. So you basically, since we'll be doing more general case, let me just write this as an integral first. We have r square integral d theta sin theta d phi at r equal to 2gm over r square. Okay, you have to basically read out from the matrix, right? Then the horizon is at fixed r, right? And you also fix t. So you just have the matrix r d theta times r sin theta d phi, right? That's what I have written here. Maybe this should be moved, right? This is visible from that side, this board. Now, okay, okay, and this gives you 4 pi times the square of this 2gm over c square. When you saw the black hole solution, you saw all factors of c and g and m, or you write in c equal to 1 units. You have seen it in with c's in. Or else this should be 1. Yeah. So I was planning to do that also. But I was telling the graduate students at ICTS that I'm going to give some lectures on black holes. The first thing they told me that if you are going to give a lectures on black holes, don't set c equal to 1 and h bar equal to 1. But I'm not going to follow their advice. Eventually, he said c equal to 1. But I thought at least for some time I'll keep factors of c and h bar. When I say c equal to 1, I'll let you know. Yes. Yeah. So this is a classical black hole, right? At this stage, you have just described a classical storage. Okay. So this picture of black hole changed in the 70s when Bekenstein and Hawking and various other people discovered that black holes are in fact not like what you think in classical theory. Once you take into account the effect of quantum mechanics, okay, they remain black, okay, but they become black body at finite temperature. So quantum effects make black hole into a black body with finite temperature. Okay. More generally, this is thermodynamic object with temperature, entropy, etc. So I'll write down the formula for the entropy that was found. The entropy. Okay, so A is the area. This is A. Kb here is a Boltzmann constant. And h bar is a Planck constant. Okay, so you can substitute this and this becomes okay. I'll write it separately. Yes.
See, you go for any about the inside of the black hole. See that here? Cool. Entropy is the it's a member of the mitosphere that corresponds to certain nuts. So what kind of mitostates are you talking about?
Yeah. Okay. So that is in fact the subject of this lecture, right? But right now, the way they discovered is not by counting microstates, but more in a thermodynamic sense. They looked at how this object, this black hole, at quantum black hole, interacts with the rest of the system, right? And based on that, they figured out that this is the entropy it carries, right? Not by counting microstates. This is more like thermodynamics rather than statistical mechanics. Okay, but I mean the question that we want to address eventually is what the microstates are of this object. Is that okay? Okay. So S then is given by Kb Cq over 4 GH bar. And from this we can calculate the temperature. So let me say how this works. So you have this, we have the thermodynamic relation D equal to TdS, right? This is the first thing we learn in thermodynamics. So in this case, E is mc square. Okay, this is Einstein's relation between energy and mass, right? If the black hole carries mass m, it has energy E. Okay. So this, using this, then we can write 1 over T as the derivative of the entropy with respect to E, which is 1 over c square the derivative with respect to m, and then we can calculate this. We have S given in terms of m. So that if I have done this calculation correctly, it's 8 pi g over c cube h bar times kbm, or T is c cube h bar over 8 pi g kb times m. Okay, this formula you might have seen. I think Subrat said he derived the black hole temperature yesterday, right? So I think this is the same formula he will have. Okay, so you can either find the entropy first and then derive the temperature, or the vice versa, right? Historically, the temperature was derived first by Hawking. So what happened is, historically what happens is that Wittgenstein predicted that there is a relation between entropy and the area with some proportionality constant, but that proportionality constant was not known, right? Because his argument was more classical. And then Hawking discovered that the black hole carries a temperature. And then once you know the black hole carries a temperature, you can integrate it back, right? You can write this equation in the reverse, and you can find the entropy as a function of the mass. Okay, so now we come to the main question that we want to address. And then in StatMech, we have this relation S equal to kb log omega, where omega is the number of microstates for a given set of macroscopic properties. Okay, macroscopic properties are something that we can measure, right? For the black hole, for example, you can measure the mass, we can measure the area, and so on, right? So you can try to fix those, okay? And then ask how many quantum states are there for this system, right? And one would expect that in statistical mechanics, there should be a formula like this: S equal to kb log omega. But clearly, this is not the way the entropy was introduced, okay? Because entropy, as I said, was introduced more from thermodynamic viewpoint. So the question that you want to address is, can we give a similar interpretation to black hole entropy? Now, if you want to do this, the first thing we need is to construct the Hilbert space. And then count states. In this case, the macroscopic property is not mass. Once you specify the mass, of course, the area gets fixed, right? So you can ask, given a black hole of mass m, can you construct its Hilbert space and count states? This requires a quantum theory of gravity. And this is where string theory comes into play, because string theory is a quantum theory of gravity. Okay, so we will try to address whether it is possible to verify that S is really kb log omega, where omega is given by the number of microstates, and we will address this within the context of string theories. Is this okay? Are there questions? Is this visible from the back? The below is too low. I can see people are struggling to see it. Is okay? This okay. Okay, this is fine, right? Okay. 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 Anyway, below that is writing is also difficult. So I think it goes both ways. So let me then say in what sense we are going to address this question in string theory. Because you have probably already seen, in fact, it is also, you will see in the string compactification lecture, that the string theory has many vacua. This is a major problem in string theory, has many vacua, which basically means the theory is unique, right? There is really one theory, right? But it has many different approximate ground states, right? Or classical ground states. Pictorially, you can think of this as if string theory has many scalars, multiple scalars, and there is a potential in that field of scalars, right? Think of the part of string theory as a scalar field theory of multiple scalars with some potential given for those scalars, and that potential has many minima. Okay, so here I am going to draw in as a function of one scalar. Okay, but you can imagine this is being a multi-dimensional field of scalars, and the potential has many minima. Okay, this is the structure that we currently understand about string theory, and around each of these minima, you can study the system, study the theory, and try to compute things. Okay, and given a minimum, we can calculate in principle all the properties that you want to calculate, right? The masses of elementary particles, what kind of elementary particles there are, and so on. But as you go from one minima to the next one, those properties change, right? Different minima give different kind of physics. And the hope is that the universe that we are living in, right, the standard model, is one of these. We don't know which one, right? We have not found a minimum which actually describes the standard model, but it's also generally accepted that the number of minima which we have actually found is very small fraction of the total number of minima that the theory has, right? Because you haven't really been able to study this potential in its full glory. So that's the way string theory tries to make connection with nature, right? That how can we get our standard model out of string theory? That hopefully one of these minima in this potential will describe exactly the standard model, right? With the correct mass of the electron, correct mass of the muon, and so on. They are what are called metastable states, right? They are not exact ground states, right? Which means that in any of these minima, right? If you are in this minima, for example, right, there is always a small probability that there will be a tunneling to the other minima. But that's not inconsistent with nature, right? As long as the tunneling rate is small enough so that the universe has survived for 10 to the 10 years, that is good enough, right, to describe our world. We don't know that we are exactly stable, right? We may tunnel to some other universe someday. So it's not necessary that the minima has to be exact ground states, right? As long as the decay lifetime is large enough, because that's the general picture. Yes. That also you don't know, right? I mean, this is related to the question of whether the number of Calabi-Yau or relevant Calabi-Yau manifolds is finite or infinite, the fluxes that we have, and so on. Right? So yeah, we don't really know very much about these questions, right? But the general hope is that one of these minima will be eventually describing us. Okay, but there is one property that is common between all these minima, and that is that gravity is always there. Each of these minima have gravity, And string theory is a quantum theory, so each of these minima actually describe a quantum theory of gravity, right. What it fails to describe is the other forces, right, because different minima have different kinds of other forces, right. Some may have some gauge fields, some may not have any gauge fields, right. Those which have gauge fields may not be the one that you want, right? But because gravity is there in all the minima, and because the black hole entropy is such a universal question, we can ask this question, right, how to explain the microscopic how to give a microscopic description of black holes. This question can be asked in any of the minima, and hopefully the answer will be universal. And if you have understood this in one minima, we may be able to generalize this to other minima. Okay. So that's the general philosophy. So this means that the question of black hole entropy in string theory can be understood, can be asked at least, even without knowing which minima describes us. And that's the philosophy we are going to try to follow. So you can ask the question about black hole entropy in any of these minima.
So can we describe this minima as a certain phase of the events?
Yeah, you can describe this in terms of phases, right? That's like ice and water. You can think of two different phases of H2O, right? There's different kind of ground states. See, each of these minima also can be thought over that way. There's different phases of the universe. So given this, our strategy will be to try to look for the simplest black hole in the simplest kind of minima. Try to solve the problem there. And then we can try to generalize it to other cases. And again, this relies on the fact that this is a somewhat universal problem, right? Because this formula that it's given by this times the area is very universal, right? In fact, it doesn't even depend on a dimension. You can just write a similar formula in any dimension. So, given that this property is so universal, one expects that if we have understood it in one of the minima, maybe that understanding will generalize to other minima as well. So, the strategy understand black hole microstates in simple black holes in simple minima. Okay, and the simplicity here depends on is defined by whether you can solve it or not, right? So, what may be simple for this problem may not be simple for other problems, right? So, what you are going to look for is what is the kind of minima that makes the problem easy to solve, and what are the kind of black holes that makes the problem easy to solve. Right? That is the strategy. Are there questions? Okay, now it turns out that the Schwarzschild is not the most convenient kind of black holes to look for, to study. And the reason can be found in this formula for the temperature that I wrote. So let me write it again. So T is C cube H bar over C cube h bar over some 8 pi g, 8 pi g kbm. Okay. So because of this temperature, first of all, the black hole radiates, because the black body radiates. As it radiates, it loses energy, and hence it loses mass, right? Because mass and energy are the same up to c square. As it loses mass, you see the temperature goes up, and hence it starts radiating more. The net result is that this system is unstable, right? If you start with a Schwarzschild black hole, it will keep radiating, and eventually, of course, it will evaporate completely. So it's not the most convenient thing to study microstates, because to study microstates is it's most useful to take a system which is stable, which remains stationary for arbitrary amount of time. So then we can carefully identify what are the states of the system and count them. This one is a time dependent system, right? Not a time independent system. So we are going to try to find a black hole which is time independent, which doesn't change as a function of time, right? With the hope that those may be the simpler systems to study. Is this clear? And this will require us to consider charged black holes. We can avoid this. Okay. Now I think I have reached the end of my ability to put in factors of C and H bar. So I'm going to set them to equal to 1. We'll see. We'll see. I'm not every charged black hole don't radiate, but there are some special charged black holes which don't radiate. Okay. So we'll set C equal to 1, H bar equal to 1, KB equal to 1. This is a Boltzmann constant. Okay. So KB equal to 1 is reasonably easy to understand what it means, right? Because KB appears only in two places. One is the expression for the entropy, one is the expression for temperature, right? In temperature, it comes as 1 over KB, in the entropy expression, it comes as KB. So when I said KB equal to 1, this basically means, so this one means that what we will call S is S over KB. And what we call T, temperature, is KB. So because if you want to restore factors of KB at the end, then in the expression for the entropy, you will multiply by KB, and in the expression for temperature, you will divide by KB. Right? That way you can restore factors of KB. H bar and C factors can be put in by dimensional analysis. So H bar and C factors can be restored by dimensional analysis. Which means that if you have gotten the final expression for anything, right, in this H bar equal to C equal to 1 unit, the actual expression will be, so the actual expression will be equal to the derived expression times, let me see the notation I have used, h bar to the alpha c to the beta. And fix alpha and beta using dimensional analysis. Okay, because without putting these factors, the dimension of the thing that you want to calculate and the actual expression that you have gotten will not match, right? And you have to fix these alpha and beta by matching dimensions. Okay. I'll illustrate this with an example, okay, how we do this, but this you can then work out in every case afterwards. See, if you use this notation, okay, then the entropy formula becomes A over 4G. Okay, you can, if you take the original formula that I gave, right, which had the C cube, H bar, KB, etc., and then set KB equal to 1, H bar equal to 1, C equal to 1, you get this formula. Now, let's see if we can recover the actual formula from this one. Suppose I have given you S equal to A over 4G. How will you recover the actual formula? So, from what I said, that this means this formula is S over KB, right, because KB appears always in this combination. Okay, there is no temperature here, so you don't have to worry about KB accompanying temperature. This is equal to A over 4G, H bar to the alpha, C to the beta. Okay, you have to find alpha and beta. So, for that, let's calculate the dimension. So, S over KB, right, this one is supposed to be log of omega, right, this is dimensionless. Right? Here, we have to find the dimension of G, right. So, let's try to calculate the dimension of G. So, force is G m1 m2 over r square, right. These are the Newton's law of gravitation, right. So, dimension of G will be dimension of force times L square m to the minus 2, right, because force times r square is L square, length square, and m to the minus 2 because there are two masses, the dimension of G. So, force has dimension mass times acceleration m L t to the minus 2 times L square times m to the minus 2. So, this gives you m inverse L cube t to the minus 2. So, let's do this then. So, S over KB, the dimension of S over KB is A over 4G. So, A has L square, 1 over G. So, that gives you m L to the minus 3 T square. Okay, this is coming from 1 over G. And then H to the alpha, C to the beta. H bar, what is the dimension of H bar? Pardon? Energy type or position momentum, right? Other one will do. If you use position momentum, then it's L times and momentum is mlt to the minus 1, right? So, H has dimension L times mlt inverse to the power alpha, and C to the beta, C is L over time, LT inverse to the power beta, right? Is it okay? So, let's just compare. So, this is dimensionless, right? So, the powers of L, M and T has to all add up to 0. So, let's do the L. So, L gives you 2 minus 3 plus alpha plus beta equal to 0. Okay, that's for L. Then for m, it is 1 plus alpha equal to 0, and for t, it is 2 minus alpha minus beta equal to 0. Right. So, this gives you alpha equal to -1, this gives you beta equal to 3, and then this is automatically satisfied. Right. So, this is a check that we have not done anything wrong. So, the actual formula then is S equal to KB A over 4G H to the alpha C to the beta. So, H bar inverse C cube. This is exactly what you had found earlier. Formula that I wrote down is exactly this. Right, but here you can just recover it from dimension analysis. So, from now on, then I am going to set H bar and C equal to 1. Right. But just to satisfy all graduate students, you have to be able to figure out the correct power of H bar and C for every formula that I write down. Okay. Okay. So, now let us go to charged black holes. We are going to deal with Einstein-Maxwell theory, and I am going to use CGS units. Okay. If you have not studied it, you have to study it, because I think that's in science we always use CGS units. Okay. So, I will try to use CGS units. So, the action, so let me write down the action with the correct normalization. You have seen Einstein's action, right? Okay, and Maxwell action also you have seen. So, it's basically Einstein plus Maxwell, right? That's the action that we start with. So, we set H bar equal to C equal to 1. And even though I am working with, I will eventually work in string theory, I am setting the dimension will be 4, okay, not because of any special reason, but 4 is more familiar. And when you study black holes in string theory, you will always compactify 6 of the dimensions and study the black holes there, right. You can also do it in other dimensions, but we will be sticking to 4, okay, just for concrete analysis. Okay, so 4-dimensional Einstein-Maxwell theory. F mu nu is, as usual, okay, where this is just derivative with respect to x mu. So, this theory has a solution. This has a charged black hole solution. Where the metric has the form The only non-zero component of F is the RT component, and this takes the form Q over R square. And we have A plus B has 2 GM, and AB is 4 pi G Q square. Okay, I have written it this way, but you can also write down the expressions for A and B explicitly. So let me write it. So A, will take A to be the larger one. So A is GM.
So Q is the most charge of the blast.
Yes, Q, you can, because the RT component, this is the electric field, goes as Q over R square. Okay, so Q is the charge of the black hole. Okay. So this differs from Schwarzschild solution, because in the Schwarzschild case, you just solve R mu nu minus half R G mu nu equal to 0, right, or R mu nu equal to 0. Here, the right hand side will contain the electromagnetic energy momentum tensor, right, because the general Einstein's equation has a energy momentum tensor on the right hand side, right, this 8 pi G T mu nu, and you have to include the contribution from T mu nu, because once you have a non-zero electric field in the background, it will produce a T mu nu. So this particular theory also has a Schwarzschild solution, right, which is a special case of this. If you set Q equal to 0, you can easily convince yourself that this becomes Schwarzschild solution. So if you set Q equal to 0, then B is 0, right, and A is 2GM. Okay, and then this becomes a Schwarzschild solution. Okay, so this is a more general version. This is called the Reis-Nordstrom black hole solution. Yeah, so the singularity, see, the R equal to 0 is always a genuine singularity, but it's surrounded by the singularity R equal to A, that's coordinate singularity. B, but B is inside A. You see, B is smaller than A. So this is also coordinate singularity, but you don't really have to worry about it, because A is the one that encloses everything, right? That is the genuine horizon. So the horizon is at R equal to A. Okay, and that's a coordinate singularity. B also happens to be a coordinate singularity.
Expression we can see the A is better than.
Yes, because there's a plus here, right? See, this is symmetric in A and B, but I have just chosen the solution where A is larger than B. Right? So R equal to A is the outer horizon. There are two horizons, exactly. So one is called outer horizon, one is called inner horizon. But from our point of view, if you are looking at the black hole from far, right, it's the outer horizon which is the relevant one, right? So R equal to A, outer horizon, and R equal to B is inner horizon. Okay, so this is not relevant for us. When the entropy is given by the outer horizon area, so entropy will be given by A over 4G. This is the outer horizon area. So this is 1 over 4G. Times 4 pi A square. Okay, so you can write this as pi over G times A is this object there. So gm plus square root is this clear? Okay, because this part remains the same, right? That's why this integral has exactly the same form. Okay, so once you have got the entropy, you can calculate the temperature. Right? So 1 over T is the derivative of S with respect to m. So this gives you 2 pi over g. 2 comes because of this 2. Then gm plus square root and then you have to take the derivative of this. That's g plus g square m over square root is clear?
G sinus C by form of
So you can define it by writing 4 pi b square. It's not clear what it means, right? Because this is not something that will be relevant when the outside interacts with the black hole. Right? So yeah, you can define an entropy associated with horizon, but it's not the physical interpretation of this is not clear. Right? Even though people have explored this in various contexts, but as I said, yeah, but again, from the outsider viewpoint, right, you only see the whole black hole, right? You don't know even that there is a cell inside. Right? So from outsider's viewpoint, the black hole horizon area is 4 pi a square. Okay, so we'll examine this formula for T, but there is one more thing that we can see from here, this formula, that this formula makes sense only when this is larger than this, right? Because otherwise A becomes complex, A and B become complex, right? If this becomes less than 0, and then the horizon doesn't exist, right? So then it's not a black hole anymore. There is a genuine singularity r equal to 0 that gets exposed. So this is what is called the bound on the mass, right? There's a bound on the mass in terms of the charge, right? So we need m square to be larger than 4 pi g q square for the horizon to exist. Now, this limit when m square approaches 4 pi g q square is called the extremal limit. So, extremal limit is m square approaches 4 pi g q square. Okay, this is the minimum mass that you can have for a given charge. G in the denominator, let me, here it is in the denominator because A over 4G, right? Oh yeah, thank you, yeah, because there is G square M square, right? 4 pi G inverse Q square. Okay, because it's G square M square that has to be larger than 4 pi G Q square. Okay, now you see that if you take the extremal limit and examine the expression for the term for 1 over T, we see that this of course goes to 0, right? But there is a GM factor that remains here. Here, this one becomes infinite. So in this limit, 1 over t goes to infinity or t goes to 0. Extremal limit, okay. Yeah. So I said that if you look at the formula for a and b, right, this is under the square root. Right. So if this number becomes negative, then a and b become complex numbers. Right. So there is really no horizon in real space. Right. As a function of r, you don't have the horizon. See, horizon is when this quantity is 0, right? And if this thing becomes less than 0, right, then this quantity doesn't vanish for any value of r. See, r is real, right? If this is complex, then r can never be equal to a. So you see from this formula, this vanishes when r is equal to a, right? Because it's 1 minus a over r times 1 minus b over r, right? See, this horizon is when this quantity is 0. And this quantity is 0 for r equal to a. But if g square m square is less than 4 pi g q square, then this is square root of a negative number. That's a complex number. So if a is complex, r can never be equal to a, right? So that means the horizon will not exist, right? As you move in the r space from infinity to 0, you will not encounter a horizon. Is that clear? So if you want a horizon, you have to have this bound. This must be larger than this. Okay, and that's where this bound came from. This extremal limit is when this quantity goes to 0. That if you set it equal to 0, you get m square is 4 pi g q square over g square. Okay, that's exactly what I have written here. Is this clear? Yes.
We might derive the S is equal to very g for the Schwarzschild black hole. So how do you know the
Yeah. So the general proof, right, that I didn't describe, right, which is due to Gibbons and Hawking, right, that shows in general that this S over S equal to A over 4G holds for all black holes. That even the S equal to A over 4G for Schwarzschild, I didn't give the proof, right? But if you have seen Suvlat's calculation of the temperature, right, you can work it backwards and get S equal to A over 4G. But there is general proof that the entropy is equal to A over 4G from what is called Euclidean gravity path integral, right? And that holds for all black holes, that including the charged ones. Any other question? Yeah, it will be like, well, it will not be like regular stars you don't expect to have singularity, right? Here, if it's less than this value, right, then this metric has a genuine singularity at r equal to 0, right? So it will be, worse than a regular star, right? It will be a singular solution. Because the Schwarzschild solution and this one has a feature that even though there is a genuine singularity at r equal to 0, you don't worry about it because there is a horizon surrounding it, so you don't see it, right? If it so happens that you go below, if this is less than this, right, then the horizon no longer exists, but the singularity at r equal to 0 still exists, right? And so it will be a singular solution, right? That's why we take this as the limit of a regular solution, right? If you want a regular solution where the all singularities are surrounded by horizon, then you have to take this inequality. Okay, but for us the important point is this, right, that in the extremal limit temperature goes to 0, and that is good because then this means that this black hole is not Hawking evaporate, right? 0 temperature, there is no radiation. So this system we expect maybe will be better suited for trying to explain the entropy because this still has non-zero entropy, right? Even if we set, yeah, here it is, right? Even if this is 0, the entropy is non-zero. So there will be something to explain, right? And this is what we'll try to explain. Clear? Pardon? At t equal to 0, yes. Right. That is important, right? So this makes it better candidate. Now it turns out that this is still not good enough. Okay, this is certainly better than earlier, but this is not good enough. We have to do something more. Okay? And it's not good enough because of the following reason. That what we see from here is that there is a Hawking radiation of this object. But imagine that this, you take a extremal black hole like this at 0 temperature, and then in quantum theory any process that is allowed will eventually happen. So if there are elementary charged particles, it can just emit a elementary charged particle which has small enough mass. It can emit that charged particle, so reduce its charge but not the mass too much, right? If the charged particle has small mass, then the charge goes down, the mass remains almost the same. So now this inequality will be violated, right? The mass remains the same, charge goes down. Okay. So this again becomes positive. We get a finite temperature, right? It starts radiating again. Maybe again comes down to 0 temperature, but then eventually it will emit another charged particle, reduce its charge and become non-extremal, start radiating again. So while it was to first approximation it was good enough, but it will not be good enough in the full quantum theory, right? Because it can decay by emitting charged particles. Is this clear? So this is where supersymmetry comes in. And this supersymmetry will now refer to in the language of the previous lecture, n equal to 2 or half. Okay, we need supersymmetry, which is n greater than or equal to 2 supersymmetry. So in a supersymmetric theory, what happens is that this, based on supersymmetry, you can put a bound on the mass of a charged particle. And that bound in supersymmetric theory, the mass of any elementary particle, any elementary or composite particle, satisfies a bound which is m which is the same as this. So this is saying that even though for the black hole we derive this bound by simply analyzing the horizon, if this black hole was a black hole in the supersymmetric theory, in an n equal to supersymmetric theory, then just based on supersymmetry we can find a bound like this. And this bound is to be satisfied, of course, by the black hole, but also by any elementary particle, anything that you can think of that you have in the theory, will have to satisfy this bound. Is this clear? This is what is called the BPS bound. If this is the case, then the scenario that you are thinking of earlier, which will make this bad, doesn't work, because this is saying that we cannot find an elementary particle whose mass is small enough for a given charge. Right? There is a bound on the mass. So imagine that they have this extremal black hole which emits an elementary particle. Right? Its mass is bounded by this. So the black hole charge reduces, but black hole mass will also reduce. and it will remain extremal. Right? You can easily check that if we emit an elementary particle from a black hole which satisfies the extremal bound, it remains extremal. Okay, and in fact the energies exactly match. Right? The mass of this becomes the mass of the final black hole plus the mass of that particle. Right? So these two really remain at rest. Right? So it cannot even go away. Because to go away, it has to have some momentum. Right? That doesn't happen. So basically, that essentially says that the black hole is stable. Right? There is no way it can decay. Is this logic clear? Okay. So if this is the case, then these are the black holes which will be the ideal candidate.
Technology details of the is
No, nothing. To derive the BPS bound, you just use the supersymmetry algebra. Completely independent. You just look at the supersymmetry algebra and derive from there.
How does this solve X?
That's the magic, right? It happens that way. That the supersymmetry algebra, the bound that the supersymmetry algebra gives, right, is exactly also the same bound that it comes from the extremal black hole. Okay, but the derivations are completely independent because it cannot be dependent because here you are talking about all elementary composite everything, right? Which have no horizon in general. Right? You don't assume existence of horizon, but nevertheless, we find exactly the same bound. Other questions? Yes.
Should we say him or like?
Yeah. So I am talking all through working on black holes on flat space time, but this kind of analysis has also been done for black holes in ADS. Right. In fact, but I am also thinking black holes in 4-dimensional flat space time, but this has been done for other dimensions as well as in ADS spaces. Right. The general principle is the same. Right. If you want to do precision comparison between microstate counting and the black hole entropy, we have to make sure that the black hole is stable enough, right? That this is not disturbed, that this doesn't decay. Let me emphasize again that this is not the kind of world we live in, right? Our world doesn't have n equal to 2 supersymmetry, right? Our world doesn't even have n equal to 1 supersymmetry. But as I explained, because the problem of understanding black hole entropy is a universal problem, that formula is universal. As I said, any black hole in any theory will have this SA equal to A over 4, right? Charge, uncharged, other dimensions. So a universal formula like that, if we can understand in any one theory, it's progress, right? And that's what we are trying to achieve. I am supposed to go on till what time? 12:40. So 10 more minutes. Okay. Now, even this at this level, right? We have set up the problem, but it looks somewhat hopeless, right? How can we even begin counting? We have a black hole solution, right? Where are the microstates, right? What do we do to count states of that system? And it turns out that here again supersymmetry comes into play, right? And I'll try to explain how supersymmetry helps us actually do the counting. Okay, not actually do the counting, but at least it will open up some ways to address this problem. Now, in the last lecture, you heard about the moduli, right? Which are problematic objects, right? If the potential is independent, but in theory, if n equal to 2 or higher supersymmetry, those are always there. Okay, which doesn't bother us phenomenologically because our world is not n equal to 2 supersymmetry, right? but it's a generic feature of theories with n equal to 2 or higher supersymmetry, that there are always flat directions, right? Which means that the potential that I drew, right, like this, there will be directions like this, but there are also directions in which this thing is flat, it does not change. Okay, so there are certain direction in the field space, this is flat. And as we also learned in the previous lecture, that those directions, the vacuum so that means that these scalars can take any vacuum expectation value, right? Their potential is completely flat. In fact, it's flat, it's not just a classical statement. You can show that even after including all quantum corrections, these flat directions are not lifted, right? They remain flat, and that means that the field can take any vacuum expectation value. Those vacuum expectation values control the various features of the theorem, like coupling constant, fine structure constant, G Newton, right? All of those are determined by what vacuum expectation value you have. So, these moduli, so certain flat directions of V exist and control G electromagnetic coupling, etc. So, by adjusting those, we can make G large, small, electromagnetic coupling large, small, and so on. Now, electromagnetic coupling large, small, electromagnetic coupling hasn't appeared anywhere in the analysis that we did, right? G appeared, right? But we had the electric charge, but the analog of the fine structure constant hasn't appeared anywhere, right? So, how does that affect us even if we can change it? So, what the electromagnetic coupling does is that it fixes the value of the minimum unit of charge, right? You know, fine structure constant, what does it fix? It fixes the electric charge of the electron, right? The physical charge of the electron. So, this fact that it controls electromagnetic coupling means that it controls the minimum unit of charge. Unit of charge, which you can call Q naught. So, this means that Q must be some multiple of Q naught. N is integer. Now, let us compare two things. One is the horizon radius, which you have calculated. Horizon radius A for extremal black hole. This was GM, because if you remember, A expression for A had a GM plus some square root. That square root vanishes for the extremal one, right? It's GM, and if you plug in the value of M, right? I have probably erased it by now. That okay, square root of 4 pi by G times Q times Q times G, that is square root of 4 pi G times 4 pi G times NQ naught. Okay, I use Q equal to NQ naught. This clear? Let's calculate the horizon radius in terms of Q, N. Now, in this case, there is one more length scale that is useful. which has nothing to do with gravity. Right? If you have a object of mass m, right? M, once you set C and L, C and H bar equal to 1, right? M has a dimension of inverse length. That is familiar to everybody? Inverse of length. The mass, energy and length are inverses of each other, right? In the H bar equal to C equal to 1 units, right? So, using M, we can calculate a length, we can construct a length which is 1 over M. Right? So, 1 over M is a length scale associated with quantum effects. And what it represents that this is a length scale in which you can reasonably localize a quantum particle of mass m. Imagine that you are trying to localize a quantum particle of mass m. Right? Can you make the position arbitrarily accurate? No, because if you try to make a position arbitrarily accurate, the momentum becomes uncertain. Right? And if the momentum becomes uncertain, the velocity also becomes uncertain, the particle flies off. Right? So, we want the particle to try to make the position as localized as possible, but not give it too much momentum, right? Because if you give too much momentum, the particle will fly off. Right? And so, this is the length scale over which you can localize a particle of mass m for a time scale of order 1 over m. Okay, because time 1 over m is also the time. Right? So, this is in quantum effects imply that we cannot localize over distance less than 1 over m for a period exceeding 1 over m. Okay, this I can give as an exercise, right? Just simple application of uncertainty principle, you can figure it out. And 1 over m in this case, so this 1 over m for extremal black hole will be square root of g over 4 pi 1 over q, which is square root of g over 4 pi 1 over n q naught. Okay, g is common between this couple. So, now we see that you have these two length scales, right, which will not compare. Right? This is the length scale of the Schwarzschild radius. This is a length scale over which you can localize a quantum particle. If this length scale is much smaller than this, that means you are able to localize a particle within its Schwarzschild radius. Then the quantum effects are not too big on the black hole, right, because the particle don't move very much, right. The horizon radius is larger than the scale over which the particle fluctuates. So, the black hole description is the better one, right. This is a good description in the limit when n q naught is large, right, when this is larger than this. But if n q naught is small, then this one is larger than this, right. This is common, g is common, 1 over 4 pi is just a number. So, if this is a very small number, then the quantum fluctuations delocalize the particle over a distance that is large enough, that is larger than the black hole horizon. Then it doesn't make sense to say that the horizon has formed, right, because the particle is fluctuating at a length scale that is wider than the horizon scale. So, we conclude from this that for n q naught much less than 1, or n q naught much larger than 1, the black hole description is good. So, you can calculate the entropy using this formula A over 4G. But if n q naught is much less than 1, well, 1 you can replace by that's square root of 4 pi or something, right? It doesn't matter. If it is much less than 1, then you should really think of this as a set of n particles, quantum particles. And small q naught, n q naught will be much less than 1, right? N, of course, we want n to be large, right? N cannot be less than 1 anywhere. N is an integer. Right? So, q naught has to be much less than 1. Q naught, as I said, is the unit of charge. Right? And unit of charge being small means that the electromagnetic coupling is small. When is the electric charge small? The electric charge of an electron is small if the fine structure constant is small. Right? So, unit of charge being small means that the interaction between these particles is weak. So, in this limit, we can describe the system as a weakly interacting quantum system of n particles. These are the constituents, because n is the number of constituents, right? The minimum unit of charge is q naught, right? So, it means that the elementary particles are carrying charge q naught, and we think of this as a collection of n elementary particles which are weakly interacting with each other. And now we have a hope of counting things. Right? This is a regular quantum system of n weakly interacting particles. Right? So, for this system, we can hope to count microstates. But this may still not satisfy us, because it is true that we can count microstates here. But this is in the regime, right? You remember that there is flat directions, right? We are varying those flat directions to go from large q naught to small q naught. Okay. So, this counting is done at some point in this along this flat direction where n q naught is small, right? So, let us say here is n q naught small. So, here is the quantum system, quantum description is valid, right? Here is n q naught large. Here you have a black hole description, right? So, you are still comparing two different things, right? This here you are calculating entropy here, and here you are counting states here. So, how can you compare that? And this is again where n equal to 2 supersymmetry plays a role. Using n equal to 2 supersymmetry, one can argue that the number of states, number of supersymmetric states or the extremal states don't change as you go from here to here. So, n equal to 2 supersymmetry or n greater than or equal to 2 supersymmetry actually relates this. So, even though we are counting two different things, right? This is the black hole where you use gravity to calculate entropy. Here, we use the standard quantum mechanics to count states. Right? N equal to supersymmetry guarantees that whatever you count here will remain here. Okay, and this is what we are going to do to compare the black hole entropy, right, that we got from gravity with actual log of the number of microstates, right? And the microstates will count here. Is this Okay, so I think this is the end of my